bonds, we care about the energy stored in chemical bonds because that is chemical energy. And we'll talk a little bit more next time about types of energy. But the energy stored in chemical bonds is called chemical energy. All right, so I have this graph over here. Let's see. This is a graph this is just from Wikipedia. This is a whole bunch of different bond energies. So this is pretty hard to see up probably back there. But if I look through, there's all these different types of bonds. So if I have a hydrogen-hydrogen bond, each of those bonds has 104 kilocalories per mole. So if I have a mole of hydrogen-hydrogen bonds, that's 104 kilocalories. Okay. So I can look up in different tables and I can figure out how much each different type of bond has, how much energy each has. So that's kind of fun. And we'll look at this on our assignment as well. So when we're thinking about chemical bonds, it always takes energy to break a bond. So what I think of is of holding a spaghetti noodle. And if I want to break that spaghetti noodle, I have to put energy into breaking the bond. Okay. So if I am putting energy in to break a bond, is this endothermic or exothermic? I'm putting energy in. Good. Endothermic. Good. So anytime I'm putting energy in, that's an endothermic chemical reaction. So always it takes energy to break a chemical bond. Okay, and then we have making a chemical bond, which is opposite. Energy always is released when we form a chemical bond. So we get energy out. It's more stable to form a bond, so we get energy out. So is making a chemical bond endothermic or exothermic? Exothermic, perfect. Hi. Thank you. You're welcome. Do you know what this is? I don't. Oh, this is the pool for Mesa. Okay.
Oh, okay.
I don't remember what reason, but it has that pool. Okay. Did we answer that? Is this endothermic or exothermic if we're forming a bond? Good, exothermic. Good. So making a chemical bond is exothermic. Breaking a chemical bond, we have to put energy in, it's endothermic. Here we talked about that. All right, when we either break bonds or form bonds, when we do a chemical reaction, we have this delta H. That tells us the heat of formation. That's what delta H stands for. So when our delta H, our heat of reaction, is positive, that means we had to put energy in. We had to add energy to our reaction. So if we have a heat of reaction that's positive, then that's endothermic. Okay. If I have a heat of reaction that's negative, that means energy was released, energy is leaving the reaction. That means it's an exothermic reaction. So you should be able to identify, just by looking at this number, this heat of reaction, if it's positive, we have to add energy, that's endothermic. If we got energy out, that's negative, that's exothermic. All right, questions so far? I still see some people writing, so I'll give you a minute. Okay, so looking at this chemical reaction, we have a heat of reaction. It's 68 kilojoules. Is this endothermic or exothermic? So it's, what, is this positive or negative? Positive, so that means we had to add energy. It's positive, we added energy, so that's going to be endothermic. Okay, how about this one? We have a negative heat of reaction. So if we add hydrochloric acid and sodium hydroxide, we're doing an acid-base reaction. Good, other way. Exo. Energy comes out. Energy is exiting. So that's exothermic. Okay, here's another one.
Endo.
Good, this one's endo. We have to add energy. That's endothermic. How about this one? Exothermic. Good. And this one? Good. Good. Okay, so we measure the heat of a reaction by using this thing called calorimetry. So we're going to watch this funny movie. I like this video. So a calorimeter, we use a calorimeter when we did the endo-exo lab. A calorimeter just measures the heat of the reaction. So let me see if I can get it. Okay, here we go.
This is the story of Threat and the one wallet that started it all. It's a story of love and adventure. And
here is a Christmas.
Now that we're done with ads.
Here is a Christmas dinner. Turkey, potatoes, gravy, delicious. But what these scientists want to know is not how it tastes, but how many calories it contains. This is Dr. Sue Roberts. Her research often involves measuring the calories in food. This is the science of a calorimeter. Firstly, you take this lovely meal and homogenize it.
Then over the course of 3 days, we slowly remove all the moisture from it in a freeze dryer, like astronaut food.
These dried samples are made into pellets. This is a bomb calorimeter.
It has a chamber into which exactly measured portions of the freeze-dried Christmas dinner is placed. The lid is sealed and electricity is fed through the food inside to explode the food and capture the heat that it produces.
Here's what's happening on the inside. Unlike in the air, in a bomb calorimeter, none of that energy escapes. It all goes into heating the water surrounding the central chamber.
So when you burn the food, it releases heat, and 1 calorie is the amount of energy that heats 1 kilogram of water by 1 degree centigrade.
When Sue and her team crunched the numbers, it turned out the full plate we saw at the beginning contained 1,208 calories.
All right. So I think that's kind of interesting. We can see. Sorry. We can see how. Let's see. How much energy is in that food by using this device called a calorimeter. Okay, so that's really how they figure out the food labels. They do some process like this to find out how many calories are in each thing that we buy. Okay, so we have this chamber. It's filled with oxygen because we are doing a combustion reaction. We want everything to burn. So we have to add some oxygen. So there's an oxygen atmosphere. Our sample's in here. And then we have some ignition wires. So you push the button and it ignites your food. Everything burns. And then we have a combustion reaction. So it's going to be exothermic. So the heat from this system moves to this water. So we have a specific amount of water in here that we've measured. And they're talking about calorie. 1 calorie is the amount of energy it takes to increase the temperature of water by 1 degree. Okay? So we can use this relationship, Q, that's the heat that's released from our food, equals the mass of the water times this constant for water. It's called the specific heat. So water increases a certain amount if you add a certain amount of energy. And then delta T is delta just means a change. So change in temperature. So we started at a certain temperature, and then after we burned our food, the water temperature is now this much. Okay. So this is how we can figure out the energy in food from those bonds. Okay. So we are going to do a lab like this. We're not going to use a fancy calorimeter. We're going to use some pop cans. We will do this after spring break. So we're going to do this on the 18th and 19th of April. So if you want to bring a food sample and figure out how many calories are in that, you can bring that food. So your class will be the 19th. I think that's a Tuesday. So we'll have this week, spring break, after spring break, and then this is the Monday. You guys will be the Tuesday after that week. Okay. All right. Questions on that? Okay. So now what we're going to do is we are going to do this packet. So it's called the bond energy packet. And this packet walks you through how to calculate a bond energy. So if you want to work together with other people, that's fine. Just make sure that you're doing your own work. These ideas will be on the test, so make sure that you understand them. Don't copy off of someone else's paper. That's not going to help you learn it.
Thank you.
Yep. And I have a key. There's a key posted, and there's a key up on the table. If as you're going, you want to check your work. So we have just under an hour to work on this. And again, I think if you work together and you kind of discuss, I think that's always helpful. So feel free to do that.